A telescope launched 3 years ago just broke our entire understanding of how the universe was born. Light from a galaxy 13.5 billion years old hit its mirrors, and what scientists saw made their models collapse. We are going to visit the farthest galaxy ever confirmed. A star factory building 180 suns every single year. A cosmic mystery so deep that astronomers are rewriting the textbooks right now. If you enjoy the journey, like and subscribe. It really helps. 13 billion years of secrets. Let's go. Close your eyes for a second and imagine a camera so powerful it can photograph a candle flame from 15,000 miles away. Now make that camera float in space. Point it at the darkest, emptiest patch of sky you can find. A patch so small it would be covered by a single grain of sand held at arm's length. Then wait and watch. That is exactly what the James Webb Space Telescope does. And what it found in that tiny dark patch of sky rewrote everything we thought we knew about the universe. The telescope launched in December of 2021. It took a month just to travel to its parking spot in space, about 1 million miles from Earth. That is roughly 4 times the distance between Earth and the Moon. Once there, it unfolded a mirror the size of a 2-car garage, 21 feet across, covered in gold, built to catch the faintest, oldest light in existence. Here is the thing most people miss. When you look through a telescope, you are looking back in time. Light travels fast, but the universe is enormous. The light hitting Webb's mirrors right now left its source millions, sometimes billions, of years ago. So every image Webb captures is a photograph of the past. This one detail changes everything. Scientists pointed Webb at galaxies formed just a few 100 million years after the Big Bang. The universe was barely a newborn. Stars were just starting to switch on for the first time. Everything was chaos and fire and gas and dark matter pulling everything together. And Webb saw it, all of it, in stunning detail. The telescope does not work like a regular camera. It sees in infrared light, which is basically heat radiation. Your eyes cannot detect infrared, but Webb can. This matters because space is full of dust clouds that block regular visible light, the way fog blocks your headlights on a dark road. Infrared slips right through that fog. Webb sees things hidden inside dust clouds that no telescope before it could ever reach. The mirror alone cost more than $10 billion to build, 10 years behind schedule. Engineers ran thousands of tests before it ever left the ground. When it finally launched, scientists held their breath for 6 months while it unfolded in space, piece by piece, in one of the most complicated engineering sequences ever attempted. One wrong fold, one stuck panel, the whole mission fails. It worked perfectly. Within weeks of turning on its instruments, Webb started sending back images that made astronomers stop mid-sentence. Galaxies where there should have been almost nothing. Massive, bright, organized structures in a universe that was supposed to be too young and too chaotic to have built them yet. The models said these galaxies should not exist at this age. The models were wrong. But here is what makes this even stranger. Webb is not seeing these galaxies as they are today. It is seeing them as they were billions of years ago, frozen in time by the speed of light. Those galaxies have lived and died and changed completely since that light left them. We are watching a ghost, an echo, a signal sent before our own sun even existed. And the message in that signal is one scientists are still trying to decode. The first clue came from something called redshift, a trick of light that tells astronomers exactly how far back in time they are looking. And what it revealed about one specific galaxy stopped the entire field cold. 13.8 billion years ago, everything that exists exploded into being from a single point, smaller than the tip of a pin. That sentence is confirmed by decades of science. But what happened in the seconds, minutes, and years after that explosion is where things get genuinely strange. The early universe was nothing like what we live in today. Picture the inside of a star, but everywhere. In every direction, no empty space, no darkness, just an ocean of plasma, so hot and so dense that even light could not move through it. Photons, the particles that make up light, kept smashing into electrons and bouncing back before they could travel more than a few feet. The universe was opaque, blind, sealed shut. This phase lasted for roughly 380,000 years. Then something clicked. The universe cooled just enough for electrons to slow down and attach to atomic nuclei. Suddenly, the fog lifted. Light could travel freely for the first time. That ancient flash of light still exists today. Scientists call it the cosmic microwave background, and Webb can detect its effects even now. But galaxies? Stars? Planets? Those were still a long way off. After that first flash of light, the universe entered a phase called the cosmic dark ages. Imagine a universe with no stars at all, just clouds of hydrogen gas, slowly drifting through cold, dark space. No light anywhere, no warmth, just gravity, silently pulling gas together, bit by bit, over millions of years. Gravity is patient. Eventually, pockets of gas grew dense enough to collapse under their own weight. The pressure at the center of these collapsing clouds became extreme. The temperature spiked, and the first stars in the universe switched on. Scientists call these the population 3 stars, and nobody has ever directly seen one. They are a confirmed theory based on physics, confirmed by math, but never photographed. The reason is simple. They burned out before any telescope existed to watch them. These first stars were enormous, likely hundreds of times more massive than our Sun, and they burned through their fuel in just a few million years before exploding. Those explosions scattered the first heavy elements across space: carbon, oxygen, iron, the building blocks of everything that came after, including you. After those first stars died, their gas and debris slowly collected into the first galaxies. Groups of millions, then billions of stars, held together by gravity and dark matter. These early galaxies were supposed to be small, scrappy, barely organized, more like loose clouds of stars than the grand spiral structures we see in today's universe. The models painted a clear picture. Early universe equals small, messy, chaotic galaxies. Organized, massive galaxies come later, much later. That picture made sense. It matched the physics. It matched every observation made before Webb launched. And then Webb looked at the early universe and saw something that picture could not explain. Massive galaxies. Organized galaxies. Galaxies so bright they should have taken billions more years to build. Sitting there, fully formed, in the infancy of the cosmos. Scientists stared at the data, ran the numbers again, checked the instruments. The data did not change. Something in the early universe built galaxies far faster than gravity alone should allow. And the answer to how begins with a number. A single measurement that tells you exactly how far back in time you are looking. Imagine you are standing on the sidewalk and a fire truck drives past you. As it comes toward you, the siren sounds high-pitched. The moment it passes and drives away, the pitch drops. The sound waves stretch out as the truck moves away from you. That stretching changes the pitch you hear. Light does the exact same thing. When a galaxy moves away from us, its light waves stretch out. Visible light shifts toward the red end of the color spectrum. The faster the galaxy moves away, the more the light stretches. The more it stretches, the redder it looks. Scientists measure this stretch and assign it a number called redshift. A low redshift number means the galaxy is relatively close. A high redshift number means the galaxy is far away, moving fast, and sending us light from deep in the past. Here is where it gets powerful. Because the universe has been expanding since the Big Bang, every galaxy is moving away from every other galaxy. The further a galaxy is, the faster it appears to be moving away from us, and the higher its redshift number. So redshift is not just a measure of distance, it is a measure of time. A redshift of 2 means you are looking at the universe about 3 billion years after the Big Bang. A redshift of 6 gets you back to about 900 million years after the Big Bang. A redshift of 10 pushes you to just 450 million years after the Big Bang. Before Webb launched, the highest confirmed redshift ever measured for a galaxy was around 13. Scientists thought that was close to the observational limit. They expected Webb to push that number a little higher, maybe to 14 or 15. Exciting, sure, but incremental. Webb smashed through that limit in its first weeks of operation. Within months of starting science observations, it confirmed multiple galaxies with redshifts above 10, then above 12, then above 13, each one older and more distant than anything previously confirmed. Astronomers were excited, but still within the range of what their models could absorb. Then one galaxy came back with a redshift of 14.44. 14.44. That number placed this galaxy at just 280 million years after the Big Bang. The universe was barely 2% of its current age. The cosmic dark ages had only just ended. The first stars had barely had time to be born, let alone explode, let alone seed the universe with enough material to build an entire galaxy. Scientists ran the redshift measurement multiple times, cross-checked it with different instruments, confirmed the spectral data from every angle. The number held. This galaxy, now called MOME Z14, formed and was already shining at full brightness when the universe was younger than the dinosaurs are old. Wrap your head around that. Dinosaurs roamed Earth for 165 million years. MOME Z14 already existed when the universe was only 280 million years old. The timeline feels impossible, and it gets stranger when you look at what this galaxy actually contains. Because MOME Z14 is not some faint smudge of early starlight. It is massive, bright, chemically complex. A galaxy that should have taken billions of years to build, sitting fully formed in the universe's infancy. And it raised one massive question. How? 280 million years after the Big Bang. Hold that number. Picture the universe as a full year on a calendar. January 1st is the Big Bang. Today, 13.8 billion years later, is December 31st. MOME Z14 lit up on January 3rd, 3 days into a 13.8 billion year story. Scientists confirmed this in 2025. The confirmation came from Webb spectroscopy instruments, tools that split incoming light into its component colors the way a prism splits sunlight into a rainbow. Each element in space leaves a unique color signature, like a fingerprint. By reading those fingerprints in the light from MOME Z14, scientists confirmed its redshift of 14.44 with certainty. Confirmed, not a theory, a measured fact. MOME Z14 is currently the most distant galaxy ever confirmed by humanity. Its light has been traveling for over 13.5 billion years to reach Webb's mirrors. By the time that light left the galaxy, our own sun did not exist. Earth did not exist. The atoms in your body had not yet come together. That light crossed an incomprehensible distance, survived the expansion of space itself, and landed on a golden mirror floating 1 million miles from Earth. And it told a story that scientists were not prepared to hear. The galaxy is bright, staggeringly bright for its age. In the early universe, gas clouds were supposed to collapse slowly into small, dim clumps of stars. The gravity needed to pull massive amounts of material together and ignite huge populations of stars takes time, billions of years of time, according to previous models. MOME Z14 skipped all of that. Here is the part that makes astronomers uncomfortable. When you measure the light from MOME Z14 and work backwards, the galaxy contains far more stars than should be possible at that age. Stars need generations of earlier stars to die first, to scatter the heavy elements that help cool gas clouds and speed up collapse. At 280 million years old, there had barely been time for even one generation of massive stars to be born and die. So where did all these stars come from? One idea gaining traction is that the very first stars, those enormous, short-lived giants from the cosmic dark ages, burned so hot and died so violently that they turbocharged the formation of everything around them. Their explosions compressed nearby gas clouds faster than normal gravity would have. That compression started a chain reaction of star birth, galaxy growth, and structure formation that happened on a timeline far faster than any model predicted. This is still a theory, confirmed by logic and physics, not yet by direct observation. But the chemistry of MOME, Z14, is already pointing in that direction. Scientists found something unexpected in the light from this galaxy. The ratio of nitrogen to carbon inside MOME Z14 is higher than what we see in our own Sunday. That unusual chemical mix is a clue, a fingerprint left behind by stars that lived and died before MOME Z14 even formed. Somebody came before. Something seeded this galaxy before it was born. And the galaxy that came next on Webb's discovery list gives an even more dramatic picture of what those early star factories actually looked like. Before Webb turned on, the leading scientific models had a clear, confident prediction. Look far enough back in time, past redshift 10, and you will find the universe in a raw, unfinished state. A few faint smudges of early starlight, thin wisps of gas just starting to collapse, the first primitive clumps of stars, scattered and dim. The universe at that age was supposed to look like a blank canvas with just a few faint pencil marks on it. Those predictions came from decades of careful science. Physicists built models using everything they knew: the speed of gravity, the behavior of dark matter, the rate at which gas cools and collapses, the time it takes for stars to ignite and grow. The math was solid. The models agreed with every observation made before Webb launched. The models said massive, bright, organized galaxies take billions of years to build. You start with small clumps. Those clumps merge over millions of years. The merged structures slowly build more stars. Eventually, after several billion years of slow growth, you get something that looks like the Milky Way. That was the accepted picture. Slow, patient, gradual galaxy formation, spread across billions of years. So when Webb pointed at the ancient universe, scientists expected to confirm that picture. They expected to see the very beginning of the process. The seeds, the raw materials, the first faint sparks before the fire. Instead, Webb found the fire already burning. Massive galaxies, fully formed structures, bright, luminous objects that should have taken 5 or 6 billion more years to build, already sitting there, complete and glowing. In the universe's infancy, the gap between prediction and reality was enormous. Scientists use a specific word when observed data breaks a theoretical model. They call it tension. The kind of tension they found here was off the charts. Some researchers initially thought the instruments were wrong. Maybe Webb's calibration was off. Maybe the redshift readings were misinterpreted. Maybe the brightness of these early galaxies was being inflated by some effect nobody had accounted for. So they checked and double-checked. Multiple independent teams ran the data, different instruments, different methods, different assumptions. The galaxies were real. The redshifts were accurate. The brightness was genuine. The standard model of galaxy formation had a serious problem, and it was not just 1 or 2 odd galaxies throwing the numbers off. Webb found dozens of these massive early structures, then hundreds. The sheer count turned a puzzle into a crisis. One anomaly can be explained away. 100 anomalies demand a new explanation. Scientists started asking a question that would have seemed absurd 5 years ago. What if the early universe had a way to build galaxies faster than gravity alone allows? What if something else was accelerating the process? The answer might involve the most violent, extreme environments in the cosmos. Galaxies that are not slowly assembling stars but detonating them. Factories running at a pace that borders on the unbelievable. And one galaxy in particular sits at the center of this mystery. A galaxy so extreme that the dust inside it glows warm enough to detect across 13 billion light-years of space. July 12, 2022. NASA released the first full science images from the James Webb Space Telescope. The world watched, scientists watched, and within hours, everything got complicated. The images were stunning. fields of galaxies stretching across a patch of sky, no bigger than a grain of sand held at arm's length. Thousands of galaxies in a single frame, spiral shapes, elliptical shapes, merging galaxies, ancient light filling every corner of the image. But the beauty was secondary. What mattered was what the data inside those images was saying. Astronomers started pulling redshift readings from the galaxies in those first frames, and the numbers coming back were high, too high. Galaxies at redshifts of 8, 9, 10, 11. Objects sitting in the universe at ages when the standard models said massive structures should barely exist. Within days of the release, papers started circulating online, scientists sharing early results, alerting each other to what they were seeing. The tone in those papers was unusual for academic science, which tends to be careful and measured. These papers were urgent. Some were almost alarmed. One team described finding a galaxy so bright and so early that its mass alone exceeded what the models said the entire observable universe should have been able to produce in stars by that point. The galaxy was too big, by a significant margin. The phrase that started circulating was simple and direct: Webb is breaking the universe. That phrase was technically an exaggeration. The laws of physics were not breaking, but the models built on top of those laws were cracking under pressure. Here is why this matters so much. The standard model of cosmology is not just a theory about galaxies. It is a unified picture of how everything in the universe came to be, from the Big Bang to the present day. Dark matter, dark energy, the rate of cosmic expansion, the formation of stars and planets, and eventually life. All of it is connected. When one part of that picture fails, the whole structure shakes. Scientists started proposing explanations immediately. Maybe star formation in the early universe was far more efficient than assumed. Maybe dark matter halos, the invisible scaffolding around galaxies, collapsed faster than the models predicted. Maybe early galaxies went through short, violent bursts of star creation that made them look bigger and brighter than they really were. All of these ideas were reasonable. All of them required changing something fundamental in the model, and none of them fully solved the problem on their own. Meanwhile, Webb kept sending data. Every new observation added more galaxies to the list. Every new redshift pushed the record higher. The challenge to the standard model grew heavier with each passing week. Scientists were forced into a position they rarely face. The data was real, the models were wrong. The question was not whether to revise cosmology. The question was how deep that revision would need to go. And then, buried in the spectral data of these early galaxies, scientists found something they genuinely did not expect: a chemical signature that pointed to a secret the universe had been keeping for 13 billion years. When scientists say a galaxy formed too early, they are not being dramatic. They mean something specific and measurable. They mean the galaxy contains more stars, more mass, and more structure than the laws of physics, as we currently understand them, should have allowed at that point in time. To understand why, you need to picture how stars form. A star is born when a cloud of gas collapses under gravity. That collapse takes time. The gas has to cool first. Cooling happens when the gas releases energy through radiation. That radiation process is slow, and the gas cloud has to be dense enough for gravity to overcome the outward pressure of the gas, pushing back against collapse. Each step in that chain takes time, millions of years per step, sometimes tens of millions. Then the star has to live long enough to produce the heavier elements that seed the next generation of stars. The first generation of massive stars burned out in just a few million years, but their explosions seeded the gas around them with carbon, oxygen, and other elements that helped the next generation of gas clouds cool faster and collapse more efficiently. So each generation of stars makes the next generation slightly faster to form. But this is still a slow process by cosmic standards. You need multiple generations of stars cycling through birth and death before you can build the kind of chemically enriched environment where thousands of stars ignite at once. Astronomers estimated this process takes at least 1 billion years, probably more, to produce a galaxy as massive and bright as what Webb found at 280 million years old. The universe, at 280 million years old, had barely finished its first generation of massive stars. It had no business hosting a fully formed galaxy, and yet, the stakes here go beyond astronomy textbooks. Our model of the universe is used to make predictions about dark matter, dark energy, and the long-term fate of everything. If early galaxy formation was dramatically faster than expected, then our measurements of dark matter behavior in the early universe need revision. And if those measurements change, calculations about cosmic expansion rates change with them. Scientists have been arguing for years about something called the Hubble tension, a disagreement between two different ways of measuring how fast the universe is expanding. Finding that early galaxies formed faster than expected adds another layer of pressure to that argument. Everything is connected. A galaxy forming too early sounds like a local problem, a cosmic footnote, but it pulls on threads that run through the entire framework of modern physics. Scientists are now asking whether something in the early universe was dramatically different from what the models assume, whether dark matter halos collapsed under different conditions, whether the very first stars were so enormous and so hot that they supercharged the environment around them in ways nobody calculated. One clue sits in the dust. Not the kind of dust on your shelf. Cosmic dust. Microscopic grains of carbon and silicate that float between stars, absorbing starlight and radiating heat. Dust that, in the earliest galaxies, was behaving in a way that made scientists look twice at their instruments. Galaxy Y1 is on fire, figuratively, but also almost literally. This galaxy existed about 600 million years after the Big Bang. The universe was still an infant, and inside this galaxy, stars were being born at a rate that makes our own Milky Way look like it has given up entirely. Galaxy Y1 produces about 180 solar masses worth of new stars every single year. One solar mass is the mass of our Sunday. So Y1 is building the equivalent of 180 suns every year, stacked together into brand new stars. That rate is extraordinary, and it has a name. Scientists call galaxies like this ultra-luminous infrared galaxies, because all that star formation generates heat, and that heat radiates outward as infrared light, so intense it outshines almost everything around it. Think of it like a factory running every machine at full speed, 24 hours a day, every day, without stopping. The heat coming off that factory would be detectable from miles away. Galaxy Y1 is that factory, but instead of machines, it is running nuclear fusion reactors, hundreds of billions of them, all igniting at once. Here is what drives that pace. When enormous amounts of gas slam together inside a galaxy, the pressure at the collision points skyrockets. Gas that would normally take millions of years to slowly cool and collapse into a star does it in a fraction of that time under this kind of pressure. Stars ignite in bursts, like a chain of firecrackers going off one after another. Scientists call these events starbursts, and Y1 is in the middle of one of the most violent starbursts ever observed in the ancient universe. Now here is the twist that nobody fully expected. All of that star formation produces enormous amounts of dust. When stars are born, they shed material. When massive stars die in explosions, they scatter dust across their surroundings. One is generating dust faster than most models predicted was possible at 600 million years after the Big Bang. Dust should not have had time to build up in such large quantities this early. Creating cosmic dust requires multiple generations of stars living and dying. It takes time, and yet Y1 is swimming in it. This creates a strange situation. The dust inside Y1 absorbs starlight and re-radiates it as heat. So the galaxy is technically glowing in infrared, but the visible starlight underneath is almost completely hidden. You cannot see the stars directly. You see only the warm glow of the dust surrounding them. It is like watching a bonfire through thick smoke. You cannot see the flames. You only see the orange glow of the smoke catching the light. Webb sees through that smoke, and what it found inside Y1 tells an even stranger story. The dust in Y1 sits at 90 Kelvin, which sounds cold. In everyday terms, that is roughly negative 292 degrees Fahrenheit, freezing by any human standard. But in deep space, where the background temperature of the universe hovers near absolute zero, 90 Kelvin is shockingly warm. The dust inside our own Milky Way is colder, significantly colder. Y1's dust is warm because the star factory below it never stops running, and the implications of that warmth, that dust, and that impossible formation rate point toward a much deeper mystery about what was really powering the early universe. Our galaxy is, by any reasonable measure, enormous. The Milky Way stretches roughly 100,000 light-years across. If you could somehow drive across it at highway speed, the trip would take longer than the current age of the universe. It contains somewhere between 200 billion and 400 billion stars. It has a supermassive black hole at its center, 4 million times the mass of our Sunday. Spiral arms curl outward from that center, carrying star clusters, nebulae, and entire solar systems in a slow rotation that takes 250 million years to complete one full lap. By any human scale of reference, the Milky Way is a monster. And yet, when you compare it to galaxy Y1 in terms of raw star production, our galaxy is barely keeping the lights on. The Milky Way creates roughly one new solar mass of stars per year. 1. Sometimes the estimates go slightly higher, maybe a few solar masses in a particularly active year, but the average is around 1. Galaxy Y1 creates 180. That is the difference between a single candle and a floodlight aimed directly at your eyes. Both produce light. The comparison ends there. This matters because star formation rate is one of the most important measures of a galaxy's activity. A galaxy that forms stars quickly is a galaxy pumping energy and mass into its surroundings at an enormous rate. It is enriching its gas supply with heavy elements faster. It is producing more radiation, more pressure, more feedback into the surrounding environment. A high star formation rate changes a galaxy's future. The Milky Way's slow, steady pace of star birth is actually one of the reasons it looks the way it does today. Calm, organized, relatively stable. The slow rate allowed structures to settle, old stars to age quietly, and the galaxy's spiral arms to maintain their elegant shape over billions of years. Galaxy Y1 had no patience for elegant shapes. Y1 was burning through its gas supply so fast that it could not sustain that pace indefinitely. Galaxies that go through extreme starbursts tend to exhaust their star-forming gas in a relatively short time, then quiet down dramatically. Scientists call this quenching. The fire burns so hot and so fast that it eventually burns itself out. What Y1 left behind after its starburst phase is unknown. The galaxy we see existed 600 million years after the Big Bang. Whatever it became over the next 13 billion years is hidden from us. Webb sees it frozen in its most extreme moment. But here is what the comparison tells us. Our slow, steady galaxy was never going to look like Y1, and Y1 was never going to end up looking like our Milky Way. These are two completely different histories, two different speeds of cosmic evolution, separated by a gap in star formation rate that is almost impossible to visualize. One solar mass a year versus 180, and both galaxies exist in the same universe, built from the same Big Bang, following the same laws of physics, which raises an obvious question. How did the same conditions produce such wildly different results? The answer starts with dust, and what the temperature of that dust is telling scientists about the engine driving Galaxy Y1. Cosmic dust sounds harmless. It sounds like the stuff you wipe off a bookshelf. The reality is more extreme. Cosmic dust fills the space between stars. It is made of tiny particles, some carbon-based, some silicate, ranging in size from a few molecules to roughly the width of a strand of human hair. These grains absorb light from nearby stars, heat up, and radiate that energy back out as infrared warmth. They are everywhere in galaxies, and they play a huge role in star formation. Dust acts like a blanket. It traps heat inside, collapsing gas clouds. That trapped heat affects how fast a cloud collapses. Too hot, and the cloud resists collapse. Cool enough, and gravity wins, and a star is born. So the temperature of cosmic dust is directly tied to the rate of star formation in a galaxy. Scientists measured the dust temperature inside galaxy Y1 and got a number, 90 Kelvin. 90 Kelvin is negative 292 degrees Fahrenheit. On Earth, that would qualify as an extreme deep freeze. The coldest naturally occurring temperature recorded on Earth's surface is around negative 128 degrees Fahrenheit in Antarctica. Y1's dust is more than twice as cold as that record, but in space, the comparison flips. The cosmic microwave background, the faint leftover radiation from the Big Bang, fills all of space at a temperature of about 2.7 Kelvin. Everything in deep space gradually cools toward that baseline over billions of years. Dust in the outer regions of modern galaxies, far from any heat source, can sit near that same freezing baseline. The dust in our own Milky Way, in regions far from active star formation, dips as low as roughly negative 423 degrees Fahrenheit. That is only a few degrees above absolute zero, the coldest temperature physically possible. Y1's dust at 90 Kelvin is dramatically warmer than that. The difference is enormous by deep space standards. What heats cosmic dust? Stars. The more stars forming nearby, the more radiation pouring into the dust, and the hotter the dust gets. One's dust temperature of 90 Kelvin is a direct readout of how furiously stars are igniting inside that galaxy. The warm dust is a thermometer, and the temperature it is reading points to an engine running at a pace that the surrounding gas supply cannot maintain forever. Here is where things get layered. Scientists studying Y1's dust temperature also noticed something about when this galaxy existed. 600 million years after the Big Bang, the universe was colder overall. Background radiation was stronger. The cosmic environment was different from today. Yet Y1's dust was still warmer than modern Milky Way dust, despite that colder cosmic background. That means Y1's internal star formation was powerful enough to override the cold of the surrounding universe. The factory was running so hot it warmed the building from the inside out. But the dust in Y1 also created a problem. All that infrared glow masks the light of the stars underneath. You cannot see what type of stars are forming. You cannot directly measure how many there are. You see only the warm red glow of the dust. Seeing through that glow required Webb to push its instruments further. And when it did, scientists found the kind of chemical fingerprint that changed the conversation entirely. Something is powering the extraordinary brightness of these ancient galaxies. The question of what, exactly, took years to untangle, and the answer reshapes how we think about the very first bursts of light in the universe. When Webb first identified galaxies at extreme redshifts, the brightness readings were puzzling. These galaxies were shining with an intensity that seemed out of proportion to their age. A galaxy 13 billion years old should be small, dim, and quiet. Instead, many of these ancient structures were outshining galaxies 10 times their expected size. Two explanations immediately landed on the table. First possibility, active galactic nuclei. This is the scientific term for the core of a galaxy where a supermassive black hole is actively consuming gas and dust. When black holes feed, they release enormous amounts of energy. The material spiraling into a black hole heats up to millions of degrees and blasts out radiation in every direction. This radiation can make a galaxy's core appear blindingly bright, sometimes outshining the rest of the galaxy combined. If the early galaxies were hosting actively feeding black holes, that would explain the extreme luminosity. Black holes do not need billions of years to build up brightness. They just need a meal. Second possibility, starbursts. Rapid, violent bursts of star formation releasing enormous amounts of light and heat. If thousands of massive stars ignite simultaneously inside a galaxy, the combined output would be extraordinary. Massive stars burn hot and bright. A galaxy full of them would glow far beyond what a quiet, slowly evolving galaxy could manage. Both explanations made physical sense, and both had a testable prediction. Black holes and stars leave different chemical fingerprints in the light they produce. A spectrometer, the kind of instrument Webb carries, can split a galaxy's light into its component wavelengths and identify those fingerprints precisely. Scientists pointed Webb's spectrometers at the most luminous early galaxies. The data came back with a clear answer for MOME, Z14. The light from that galaxy carries the signature of stars, not a black hole. The specific wavelengths, the ratios of different elements in the spectral readout, match what you would expect from a massive population of hot, young stars burning simultaneously. This is confirmed. Scientists measured it directly. So MOME, Z14's extraordinary brightness comes from stars, enormous numbers of stars, all burning at once, in a galaxy that formed just 280 million years after the Big Bang. Stars that should not have had time to exist in such numbers. And if the brightness comes from stars rather than a black hole, then the mass estimates for MOME, Z14, are real. The galaxy genuinely contains the stars its brightness implies. The mass is there. The structure is there. The chemical complexity is there. All of it built in a tiny fraction of the time the models allowed. This finding closed one door and opened several others. If stars are responsible, then something was making stars form faster, more efficiently, and in greater numbers than any model accounted for. Something in the early universe was supercharging the process. The clue to what that something might be was hiding in the chemistry of MOME, Z14's light, a chemical ratio that matched something much closer to home. The universe is full of walls. Clouds of cosmic dust hang between stars, between galaxies, across the arms of the Milky Way and the halos of ancient structures, billions of light years away. Visible light, the kind your eyes detect, cannot pass through these clouds. The dust absorbs it, scatters it, blocks the view completely. Every telescope before Webb ran into this problem. You would point a telescope at a distant galaxy, only to find a thick curtain of dust in the way. The galaxy was there, the science was there, but the view was blocked. Infrared light changes the game. Infrared sits just beyond the red end of the visible spectrum. Your eyes cannot see it, but everything warm emits it. A cup of coffee, a human body, a star nursery buried inside a dust cloud. Infrared radiation passes through cosmic dust with far less interference than visible light. Think of it like sonar. A submarine sends out sound waves that travel through water and bounce back off objects the crew cannot see. Visible light is like a flashlight beam that fog scatters in every direction. Infrared is the sonar signal that cuts through the fog and bounces back useful information. Webb was built entirely around this advantage. Its primary mirror, 21 feet across and coated in a layer of gold, just a few atoms thick, captures faint infrared signals from sources billions of light years away. The gold is not decorative. Gold is one of the best reflective materials for infrared wavelengths. Every photon counts when you are trying to detect the faint warmth of a galaxy that formed 13 billion years ago. Behind that mirror sits a suite of instruments designed to detect infrared light across a wide range of wavelengths. Some instruments capture images. Others split the incoming light into a spectrum of colors, like a prism, so scientists can read the chemical fingerprints hidden inside. But infrared detection creates its own problem. Infrared is heat radiation, and everything that has any warmth at all emits infrared, including the telescope itself. If Webb's own mirrors and instruments were anywhere close to room temperature, they would glow so brightly in infrared that they would drown out every faint signal from the distant universe. So the entire telescope had to be kept cold, extremely cold. Webb carries a 5-layer sunshield the size of a tennis court. Each layer reflects and radiates away heat from the sunday. The sunshield keeps the telescope's instruments at roughly -387 degrees Fahrenheit, colder than anything in our solar system, except the dark craters at the poles of the moon. This temperature allows Webb's detectors to catch signals so faint they carry only a handful of photons, individual particles of light that have been traveling for over 13 billion years. Ancient messengers from the dawn of the cosmos, arriving one photon at a time, without the ability to see in infrared. MOM Z14 would be invisible. Y1 starburst would be hidden behind its own dust. Dozens of ancient galaxies discovered in Webb's first years would remain completely unknown. The infrared view opened a window that visible light had kept shut for the entire history of astronomy. And one of the most surprising things visible through that window was not the brightness of early galaxies, or their size, but the shape of them. Every time Webb captures an image of MOM Z14, something genuinely hard to process is happening. The light in that image left its source 280 million years after the Big Bang. It entered space and started traveling. The universe expanded around it as it traveled, stretching the light's wavelength from visible blue into deep infrared. The galaxy that produced it aged, changed, possibly died, possibly merged with others. Stars in that galaxy were born and exploded billions of years ago, and the photons kept traveling through the void between galaxy clusters, through the large-scale structure of the universe, the cosmic web of filaments and voids, past billions of galaxies that formed, evolved, and aged over the course of that journey, through the outer edges of our own local group of galaxies, through interstellar space, across the final million miles to where Webb sits, orbiting a gravitational balance point between Earth and the Sunday. The photons arrived, hit the gold mirror, triggered a detector, became data. The journey took 13.5 billion years. To put that in terms closer to home, when those photons left MOM Z14, our Sun did not exist. Earth did not exist. The atoms that would one day form our solar system were still scattered across the universe, locked inside stars that had not yet died. The entire 4.5 billion year history of our planet, every single event from the formation of the oceans to the rise of human civilization, all of it happened after those photons were already billions of years into their journey. By the time you were born, that light was 13.5 billion years old and almost home. This creates a strange paradox. When scientists say they are observing MOM Z14, they are observing a ghost. The galaxy they see is the galaxy as it existed 13.5 billion years ago. Whatever it looks like right now, today, in this moment, is completely unknown. It could be 10 times larger. It could have merged with other galaxies and become unrecognizable. It could have burned through its star-forming gas and gone quiet. It could have collided with something and been torn apart entirely. We are looking at history, not the present. And the history captured in that ancient light shows a galaxy blazing at full brightness in a universe that should have been too young to produce it. There is one more layer to this, because the universe has been expanding since those photons left MOM Z14. The galaxy itself is now much further away than 13.5 billion light-years. Space expanded around the photons as they traveled, carrying the source of the light even further away. Scientists calculate that MOM Z14 is currently about 30 billion light-years away from Earth, even though the light we detect is only 13.5 billion years old. The universe is larger than the age of the light traveling through it. That fact alone is one of the stranger consequences of cosmic expansion. Webb is effectively a time machine. Every image is a fossil, and the fossils it is finding are forcing scientists to confront something they built their careers around assuming was true. The early universe was far more organized than anyone expected. For decades, the textbooks agreed on one thing: spiral galaxies take billions of years to form. The graceful, organized disk shape of a galaxy like our Milky Way requires a long, slow, settling process. Gas has to cool and spin down into a flat plane. Stars have to form in organized waves. The disk has to survive without being shattered by collisions and mergers. The prediction was clear. In the early universe, you would find no disks. You would find blobs, irregular clumps of stars, chaotic and unstructured, beautiful in their own raw way, but nowhere close to the organized spiral structures that define the modern universe. Astronomers called this the Hubble sequence, the idea that galaxies start messy and gradually sort themselves into organized forms over billions of years, irregular first, elliptical next, spiral last. And spirals, the most organized form, were expected to appear no earlier than about 6 billion years after the Big Bang. Webb found fully formed disk galaxies 1 billion years after the Big Bang, confirmed, directly observed, with clearly defined disk structures, organized star populations, and the geometric regularity that the models reserved for a much older universe. This finding hit the field hard. Disk galaxies require calm conditions to maintain their shape. A major collision with another galaxy of similar size can destroy a disk completely, converting it into a featureless elliptical blob. In the early universe, galaxies were colliding and merging constantly. The density of the early cosmos meant structures were packed more tightly, collisions more frequent, the environment more violent, and yet some early galaxies maintained perfect disk structures through all of it. How? One emerging idea is that the first disk galaxies formed through a different process than later ones. Instead of growing by merging with other galaxies, some early galaxies grew by steadily pulling in smooth streams of cold gas flowing along dark matter filaments. This process, called cold flow accretion, allows a galaxy to grow in mass without the violent disruption of a merger. The gas arrives smoothly, settles into a disk, and forms stars in organized waves without shattering the structure. This is a theory, supported by some simulations, but not yet fully confirmed by direct observation. But it provides a plausible path for disk galaxies to form and survive in a chaotic early universe. What is confirmed is the observation itself. Disk galaxies existed 1 billion years after the Big Bang. The old timeline was off by 5 billion years. That kind of error is remarkable. It means every model predicting galaxy morphology in the early universe needs revision. The parameters that govern how gas cools, how dark matter halos spin, and how collisions affect galaxy shape all need to be revisited. The disk galaxy discovery was not a footnote. It was a direct strike at one of the core assumptions of galaxy evolution theory. And the oldest star clusters circling our own galaxy today might be carrying a message about where those ancient disks came from, written in their chemistry for anyone patient enough to read it. A spiral galaxy is fragile. That sounds strange to say about an object containing hundreds of billions of stars and spanning tens of thousands of light years. But structurally, a galactic disk is delicate. It holds its shape only when conditions allow it to. Disrupt those conditions, and the disk falls apart. The specific disruption scientists worried about most was mergers. When two galaxies of similar size collide and merge, the gravitational interaction is catastrophic for disk structure. Stars from both galaxies get flung into wildly different orbits. The organized rotation that defines a disk collapses into a scramble of random trajectories. The end result is almost always an elliptical galaxy, smooth and featureless, like a cosmic bruise left behind by a violent collision. The early universe was a collision zone. At 1 billion years after the Big Bang, galaxies were forming close together, embedded in dense networks of dark matter filaments. Gravity was pulling everything toward everything else. The merger rate in the early universe was dramatically higher than it is today. Modern galaxies occasionally collide. Ancient galaxies were colliding constantly. So seeing intact disk galaxies at 1 billion years after the Big Bang raised an obvious problem. How did these disks survive? One part of the answer involves dark matter. The invisible scaffolding that surrounds galaxies, called the dark matter halo, plays a major role in shaping the galaxy's rotation and protecting its structure. A massive, well-organized dark matter halo can stabilize a disk galaxy against disruption. If early dark matter halos collapsed and organized faster than expected, they could have provided that stability earlier than any model predicted. This is still theoretical, But the gravitational evidence for dark matter halos is solid, and their role in galaxy stability is well established. The question is whether they organized quickly enough to explain what Webb is seeing. A second part of the answer might involve the type of mergers happening in the early universe. Major mergers, two large galaxies of similar mass crashing into each other, are destructive. Minor mergers, a large galaxy absorbing a much smaller one, are far less disruptive to disk structure. If early galaxies grew primarily through minor mergers and cold gas accretion rather than major collisions, their disks could have survived. But even this does not fully explain the number of intact disks Webb is finding. Some scientists are now seriously entertaining an idea that would have been dismissed a decade ago. Maybe the physics of the very early universe allowed disk galaxies to reform rapidly after disruption. Maybe the high density of star-forming gas in the early cosmos allowed disrupted disks to reassemble faster than anything in the modern universe could. If true, that changes every simulation of early galaxy evolution. The disk galaxy problem is one of several places where Webb's data keeps pointing at the same conclusion. Something in the early universe was more organized, more efficient, and more structured than the standard models allowed. And that organization left a fingerprint, a chemical one, buried inside the light of Mohm, Z14, written in elements heavier than anything the Big Bang produced. Every atom in the universe has a story. The lightest elements, hydrogen, helium, and tiny amounts of lithium, were forged in the Big Bang itself. Everything heavier than that, carbon, nitrogen, oxygen, iron, every element in your body, had to be built inside stars and scattered by stellar explosions. This process is called nucleosynthesis. It is confirmed physics. It explains the entire periodic table of elements. But nucleosynthesis takes time. A star has to form. It has to live for millions or billions of years, fusing lighter elements into heavier ones in its core. Then it has to die, either in a quiet fade or a violent explosion, to scatter those heavy elements into surrounding space. The next generation of stars forms from that enriched material. They build more heavy elements, explode again, enrich the next generation further. Each cycle takes millions of years, sometimes hundreds of millions. So when Webb analyzed the light from Mohm Z14 and found heavy elements in unexpected ratios, scientists paid very close attention. The specific measurement was the ratio of nitrogen to carbon. In most stars, including our Sun, nitrogen and carbon appear in roughly predictable proportions. The ratio reflects the nuclear processes running inside stars of typical mass and age. Mohm Z14 has a nitrogen to carbon ratio higher than what we see in our Sunday, significantly higher. This is confirmed by direct spectral measurement. The fingerprint is in the light. A high nitrogen to carbon ratio is the signature of a specific kind of stellar environment. It points to stars that were extremely massive, burning at extreme temperatures, processing material through nuclear reactions fast enough to produce unusual nitrogen enrichment. Stars that lived violently and briefly. Here is what made scientists stop cold. This exact same chemical signature, this unusual nitrogen to carbon ratio, appears in the ancient globular star clusters orbiting the Milky Way today. These clusters are among the oldest objects in the universe. They formed billions of years ago and have orbited our galaxy ever since, like fossil records floating in our cosmic backyard. Mohm Z14 at 13.5 billion light-years away, and the ancient globular clusters surrounding our own galaxy are carrying the same chemical fingerprint, the same ratio, the same unusual enrichment, the same story written in nitrogen and carbon. This similarity tells scientists something profound. The environments that produced our oldest local star clusters look remarkably like the environment inside Mohm Z14. Both places saw rapid, extreme star formation early in the universe's history. Both were shaped by the same kind of massive, short-lived stars burning through unusual nuclear cycles. The ancient star clusters orbiting the Milky Way right now may be direct descendants of galaxies like Mohm Z14. survivors of the earliest, most violent era of cosmic history. Remnants of a time when the universe was building itself faster than anyone thought possible. And what powered that extreme early star formation points to something even more astonishing. Stars so large and so bright that no human instrument has ever directly observed one. Stars that may have been the most extreme objects the universe has ever produced. The oldest objects in our galaxy have been orbiting the Milky Way for over 12 billion years. They are called globular clusters, dense balls of ancient stars, some containing hundreds of thousands of suns packed into a sphere roughly 100 light-years across. Imagine a school of fish, but instead of fish, it is 300,000 stars. And instead of an ocean, it is a region of space smaller than the distance from Earth to the nearest star system. They hang in the halo above and below the Milky Way's disk, tracing slow orbits that take hundreds of millions of years to complete. They are fossils, survivors from the earliest chapters of cosmic history, carrying the chemical composition of the environments where they formed. For decades, astronomers studied their chemistry. The unusual ratios of certain elements inside globular cluster stars pointed to a violent, extreme origin. These stars formed in environments that saw rapid, intense nuclear burning, environments where massive stars cycled through their lives in just a few million years, seeding the gas around them with unusual elemental ratios before dying in spectacular explosions. Scientists understood the chemistry. They just did not know exactly where those environments existed or what they looked like. Then Webb read the chemistry of MOM Z14 and found an answer. The nitrogen to carbon ratio inside MOM Z14 matches the ratio inside those ancient globular clusters. This match is striking because these two objects exist across an almost incomprehensible distance of space. MOM Z14 sits 13.5 billion light-years away. The globular clusters orbit our galaxy at distances ranging from a few thousand to a few 100,000 light-years. Same fingerprint, same unusual enrichment, same evidence of the same extreme stellar processes running at the same furious pace. The straightforward interpretation is powerful. The kind of environment inside MOM Z14, dense, extreme, building stars at explosive rates through the action of massive short-lived stars, is the same kind of environment that produced the globular clusters now orbiting our galaxy. Some of those clusters may even be relics of galaxies like MOM Z14 itself, ancient galaxies that formed early, burned bright, and were eventually absorbed into larger structures as the universe aged. Their star clusters survived the mergers, preserved in orbit around the galaxies that consumed them. The globular clusters hanging around the Milky Way today could be fragments, survivors from the first chapter of cosmic history, carrying a chemical signature that matches the most distant galaxy ever confirmed. This connection matters for one specific and concrete reason. It gives scientists a way to study the early universe without needing to see it directly. The chemistry locked inside nearby globular clusters reflects conditions from 13 billion years ago. It is a fossil record orbiting our own galaxy. And that fossil record now has a confirmed match in the most ancient structure Webb has ever photographed. Every ancient cluster orbiting the Milky Way carries a story from the universe's infancy. A story that, until Webb, nobody could read clearly. The story points to stars that were unlike anything alive in the universe today. Stars so massive, so hot, and so short-lived that they may have been responsible for lighting up the early cosmos faster than any model expected. What those stars looked like, how they formed, and why they no longer exist is the next piece of this puzzle. MOM Z14 did not build itself from scratch. That is the conclusion sitting quietly inside the nitrogen to carbon data. The chemical signature inside MOM Z14 is the fingerprint of stars that lived and died before MOM Z14 even formed. Stars that seeded the surrounding gas with unusual elements, altered the chemistry of the environment, and set the conditions for everything that came after. This means there was a generation before the generation we can see. Scientists call this the pre-enrichment problem. For a galaxy at 280 million years old to carry the chemical complexity that MOME Z14 shows, something had to come first. Something had to live fast, burn hard, and die violently, leaving behind a chemically enriched environment that MOME Z14 then formed inside. The timeline is almost absurdly tight. The Big Bang produced hydrogen, helium, and almost nothing else. The first stars formed from that pure material somewhere between 100 million and 200 million years after the Big Bang. These first stars were enormous. They burned through their fuel in just a few million years. Then they exploded. Those explosions took the pure hydrogen and helium environment of the early universe and laced it with heavier elements for the first time. Carbon, nitrogen, oxygen, neon, heavier things, still forged under the extreme pressures of the dying star's core. MOME Z14 formed out of gas that had already been through this process. Gas that had already been enriched by at least one generation of massive stars dying before it. All of that had to happen inside 280 million years. Think about the compression of that timeline, from the Big Bang to pure hydrogen clouds, to the first massive stars switching on, to those stars burning out and exploding, to their debris cooling and collapsing into a second generation of structures, to MOME Z14 forming and growing large enough to glow brightly across 13.5 billion light-years of space. 280 million years. For comparison, Earth has existed for 4.5 billion years. The time from the Big Bang to MOME Z14 is less than a tenth of Earth's current age. It is a geological eye blink on a cosmic scale. The pre-enrichment implied by MOME Z14's chemistry tells scientists that whatever came before moved extraordinarily fast. The first generation of stars had to form quickly, burn out quickly, and enrich their surroundings quickly enough for MOME Z14 to form in the compressed window that the redshift data allows. This is where the theoretical picture of the very first stars becomes critical. Scientists call them population 3 stars, and they represent one of the last truly unobserved chapters in cosmic history. Nobody has ever directly seen one. They are predicted by physics, required by chemistry, demanded by the logic of the timeline. But the universe's first generation of stars burned out before any telescope existed, and their direct light is almost certainly beyond Webb's reach. Almost. Because Webb is getting closer to the era when those first stars switched on, and what scientists understand about their size and behavior is extraordinary enough to reshape the entire story of the early universe. What those stars looked like makes everything else we have discussed seem almost ordinary. The first stars in the universe were monsters. This is a confirmed scientific prediction built on well-tested physics, and it fundamentally changes how we understand everything Webb has found. In the very early universe, the gas available for star formation was almost pure hydrogen and helium. No carbon, no oxygen, no heavier elements. And that matters enormously because heavy elements play a critical role in the star formation process. They absorb radiation from nearby stars, cool the surrounding gas, and help gas clouds fragment into smaller pieces. Smaller fragments collapse into smaller stars. Without heavy elements, the gas clouds in the early universe could not fragment efficiently. They stayed large. They collapsed as enormous single units rather than breaking apart into many smaller stars. The result was stars of a size the modern universe almost never produces. Scientists calculate that the first generation of stars, called population 3 stars, ranged from roughly 10 times to potentially several hundred times the mass of our Sunday. Some theoretical models suggest individual stars could have reached 1,000 times the solar mass, burning at temperatures so extreme that the radiation they produced was powerful enough to ionize entire regions of surrounding space. 1,000 solar masses in a single star Our sun would fit inside one of these stars the way a marble fits inside a basketball. Except the basketball is so hot that the radiation pressure alone prevents anything from approaching it. These were objects of almost incomprehensible energy output, burning through their fuel so fast that their entire lifespan measured in the low millions of years. For context, our sun will live for roughly 10 billion years. A star 1,000 times its mass burns out in a few million years, 10,000 times faster, and when these first stars died, they did not go quietly. Stars above roughly 40 times the mass of our sun do not produce ordinary supernovae. They collapse so violently that the explosion is called a hypernova, releasing energy many times greater than a standard stellar explosion. Some of the most massive stars may collapse directly into black holes without a visible explosion at all, swallowing their heavy elements rather than scattering them. This creates a problem. If the first stars were so massive they collapsed into black holes without exploding, how did their heavy elements get into the surrounding gas to enrich the next generation? The answer lies in the range. Some first-generation stars were massive enough to produce hypernovae, but not quite massive enough to collapse silently. These stars in the sweet spot of the mass range exploded violently and scattered their enriched material across enormous distances. That scattered material became the seed for everything that followed, including MOME Z14. Scientists now believe Webb may be approaching close enough to the first stellar epoch to detect indirect evidence of population, 3 stars, through the chemical imprints they left in subsequent structures. MOME Z14's unusual nitrogen-to-carbon ratio is potentially one of those imprints. The monsters that lit the early universe may have left a signature in the most ancient galaxy ever confirmed, but understanding what powered the extraordinary brightness of that galaxy required scientists to confront a completely different question, one they thought they already had the answer to. When Webb started sending back images of blindingly bright early galaxies, the first instinct of most astronomers was the same: black holes. Supermassive black holes sitting at galaxy centers and actively consuming material are some of the brightest objects in the universe. When a black hole feeds, the gas and dust spiraling toward it heats up to millions of degrees. That heated material releases radiation across the entire electromagnetic spectrum, from radio waves to X-rays. A single actively feeding supermassive black hole can outshine every star in its host galaxy combined. These feeding black holes are called active galactic nuclei, and they are known to exist even in the early universe. Scientists have confirmed supermassive black holes, billions of times the mass of our sun, existing less than 1 billion years after the Big Bang. Finding active galactic nuclei powering the brightness of early galaxies would have fit comfortably into existing models. It would have been the clean explanation, the familiar one, and it would have been less alarming than the alternative. If black holes are responsible for the brightness, you do not need to produce enormous numbers of stars rapidly. You just need one massive black hole feeding aggressively. Black holes can grow through accretion, pulling in material and releasing energy without requiring the careful, generation-by-generation buildup of stellar populations. The black hole explanation would have let the standard model of galaxy formation survive mostly intact. Early galaxies look big and bright because they host luminous feeding black holes, not because they formed impossibly large populations of stars ahead of schedule. Scientists wanted this explanation to work. Several early papers argued in its favor. Some observations of early bright objects did show signatures consistent with active galactic nuclei. The debate was real, but for MOME Z14 specifically, something did not fit. The black hole feeding explanation makes a specific prediction about the spectrum of light coming from a galaxy. Actively feeding black holes produce a characteristic signature in their spectra. Certain emission lines, specific wavelengths of light produced by highly ionized gas superheated near the black hole, appear in predictable patterns. The ratio of different emission lines tells a trained astronomer immediately whether they are looking at a star-dominated galaxy or a black hole-dominated one. Webb's spectrometers are precise enough to read these signatures from 13 billion light-years away. And when scientists read MOME Z14's spectrum carefully, the black hole signature was not dominant. The emission line ratios pointed clearly towards stars. Hot, young, massive stars producing ionizing radiation at extraordinary rates. Stars burning with the particular intensity that massive early stars are predicted to produce. The spectrum matched stellar populations, not an active galactic nucleus. This was not the answer scientists were hoping for. A star-powered galaxy at that brightness and that age meant the stars were really there. The mass was real. The timeline was real. The crisis in the standard model was real. The clean explanation evaporated, and what replaced it required a completely new picture of what kind of stars could produce enough light to make MOME Z14 shine the way it does across 13.5 billion light-years of space. Science runs on measurements. And the measurement that settled the black hole debate for MOME Z14 came from one of the most powerful tools Webb carries. A spectrograph takes incoming light and splits it into its component wavelengths. The result looks like a rainbow stretched across a detector, but with dark lines and bright lines interrupting the smooth gradient. Those lines are the fingerprints of specific atoms. Each element absorbs and emits light at precise wavelengths that never change. Hydrogen always leaves its mark in the same place. Carbon always leaves its mark in the same place. Nitrogen, oxygen, silicon, every element has a fixed address in the spectrum. By reading those addresses, scientists can determine exactly what a galaxy is made of and what kind of energy source is producing its light, all from billions of light-years away. This is confirmed physics. It has been used since the 19th century, when scientists first pointed prisms at the sun and began reading the solar spectrum. Webb's spectrograph is orders of magnitude more sensitive than anything that came before it. It can detect individual emission lines from a galaxy so distant that the light arriving at its detectors carries only a handful of photons per hour. When scientists analyzed MOME Z14's spectrum in detail, they focused on specific emission lines that serve as diagnostic tools. The ratio of particular nitrogen, carbon, and oxygen lines tells astronomers whether the ionizing radiation in a galaxy is coming from a very hot stellar population or from an actively feeding black hole. Active galactic nuclei produce a specific pattern. The gas around a feeding black hole reaches temperatures of millions of degrees. At those temperatures, atoms get stripped of multiple electrons simultaneously, producing emission lines from highly ionized species that stars alone cannot generate. MOME Z14's emission lines did not match that pattern. The lines matched the pattern produced by a population of extremely hot, massive stars. Stars with surface temperatures of 50,000 to 100,000 degrees, radiating enormous amounts of ultraviolet light that ionizes the surrounding gas and produces the specific emission line ratios scientists measured. This is a confirmed result, peer-reviewed, checked by multiple independent teams. The light from MOME Z14 comes from stars. Massive, hot, young stars burning at extreme temperatures in enormous numbers, creating the kind of ionizing radiation field that only dense clusters of the universe's most powerful stellar objects can produce. The confirmation had an immediate consequence. If stars are producing that light, then MOME Z14 genuinely contains the stellar mass its luminosity implies. Estimates place the galaxy's stellar content at somewhere between 500 million and a few billion solar masses. In a galaxy that is only 280 million years old, that mass had to form from gas. That gas had to cool and collapse. That process had to run at a pace far beyond anything the standard models allowed. The spectral data confirmed the crisis, and it pointed directly toward a mechanism that most cosmological models had significantly underestimated. Something in the early universe was accelerating the entire process of structure formation. Something invisible. Something that left no direct light for Webb to detect, but whose gravitational fingerprint is stamped all over everything it built. You cannot see dark matter. You cannot touch it. You cannot detect it with any instrument designed to catch light. But without it, galaxies cannot form at all. Dark matter is confirmed to exist through its gravitational effects. Scientists have measured the way it bends light, the way it holds galaxy clusters together against the force of cosmic expansion, the way it shapes the rotation curves of spiral galaxies. The evidence is overwhelming. Dark matter makes up roughly 27% of the total energy content of the universe. What dark matter actually is, at a particle physics level, remains one of the biggest unsolved mysteries in science. But its behavior at large scales is well understood, and its role in galaxy formation is central. In the early universe, dark matter was not smoothly distributed. Quantum fluctuations from the Big Bang created tiny variations in density. Some regions had slightly more dark matter than others. Gravity amplified those variations over time. Regions with more dark matter pulled in more material. They grew denser. Eventually, they collapsed into structures called dark matter halos, roughly spherical clouds of dark matter that provided the gravitational scaffolding for galaxies to form inside. The process is well established. Regular gas, hydrogen and helium, falls into dark matter halos. The gas cools and condenses at the center. Stars form. A galaxy grows. The timeline of this process depends on how quickly dark matter halos collapse and how efficiently gas cools inside them. Standard models predicted a specific pace, a specific schedule for when halos of different sizes would form and begin hosting galaxies. Webb's observations suggest the schedule was wrong. The galaxies Webb found in the early universe, massive and organized at 1 billion years after the Big Bang and even earlier, required dark matter halos that collapsed significantly faster than the models predicted. Either the halos formed faster, or the gas cooling inside them was dramatically more efficient, or both. One proposal gaining attention involves the initial density variations from the Big Bang. If those variations were slightly larger than standard models assume, dark matter halos would have collapsed earlier and more quickly. A small change in the initial conditions of the universe could cascade into dramatically faster galaxy formation across the entire cosmic timeline. This is a theory, but it is testable, and it connects to a much larger debate about the parameters of the early universe that physicists have been wrestling with for years. Another proposal involves the interaction between dark matter and ordinary gas in the early universe. If dark matter halos in the early cosmos had slightly different properties than in modern halos, they may have provided stronger gravitational focusing for infalling gas, speeding up the cooling and collapse process. Both proposals require changing something fundamental about the early universe's physics, and neither one fully accounts for the sheer number of massive early galaxies Webb keeps finding. The problem is bigger than any single galaxy anomaly. It is a population crisis. One impossible galaxy is a puzzle. 100 impossible galaxies is a catastrophe for the model. That is the situation astronomers found themselves in after Webb's first 2 years of operation. The earliest images showed a handful of surprisingly bright, surprisingly massive early galaxies. Scientists could debate each one individually. Maybe this one has an unusually efficient star formation history. Maybe that one is being gravitationally lensed and appears brighter than it really is. Individual cases always allow room for alternative explanations. But Webb kept looking, and the count kept climbing. Dozens of galaxies with redshifts above 10, many with masses far exceeding what standard models allowed at those ages. Several with organized structures showing disk features that should have taken billions more years to develop. All of them confirmed by independent spectroscopic measurements. The population was real. The anomaly was systematic. Scientists began running statistical analyses. They calculated how many massive early galaxies the standard cosmological model predicted should exist in a given volume of the early universe. Then they compared that prediction to what Webb actually found. The observed count exceeded the predicted count by a significant margin. In some mass ranges and redshift ranges, Webb found several times more galaxies than the model allowed. A factor of several times is not a rounding error. A factor of several times means the model is missing something fundamental about how quickly galaxies assemble mass in the early universe. The problem has a specific technical name in cosmology. The stellar mass density of the universe at high redshift appears to be too high. There is simply more stellar mass at early times than the standard formation history can account for. For this to make sense, one of three things must be true. Either the early universe converted gas into stars far more efficiently than the models assumed, or dark matter halos collapsed and organized far earlier than predicted, or the models are measuring galaxy masses incorrectly due to some systematic error in how astronomers interpret early galaxy light. All three options are being actively investigated. The efficiency argument has gained the most traction. Standard models assume that only a fraction of the gas inside a dark matter halo ever converts into stars. The rest gets blown out by stellar feedback, the radiation and winds from newly formed stars that heat surrounding gas and push it away from star-forming regions. If early galaxies had weaker stellar feedback or more efficient gas conversion, the stellar mass problem could ease considerably. Some simulations suggest that, in the dense, compact, high-pressure environments of early galaxies, stellar feedback was less effective at pushing gas away. The gas was too dense, the gravity too strong, the star formation happening too fast for feedback to shut things down before enormous stellar masses had already built up. These simulations are promising. They are also incomplete. They depend on assumptions about stellar physics in environments that have never been directly observed. The population problem remains open, and it points toward a question that cuts to the heart of modern cosmology. The standard cosmological model has a technical name. Scientists call it lambda cold dark matter, or lambda CDM for short. Lambda represents dark energy, the force driving cosmic expansion. Cold dark matter refers to the slow-moving dark matter particles that provide the gravitational skeleton for everything that forms. This model is the most successful scientific framework ever built for describing the large-scale structure of the universe. It correctly predicts the pattern of galaxy clusters and voids across billions of light-years. It accurately describes the cosmic microwave background. It accounts for the observed expansion rate of the universe. It has passed hundreds of independent tests across decades. It is also based on Webb's observations, producing predictions for the early universe that do not match reality by a meaningful margin. The specific failure involves a quantity called the halo mass function. This is a mathematical description of how many dark matter halos of each mass should exist at any given time in the universe's history. It follows directly from the initial conditions of the Big Bang and the behavior of dark matter under gravity. The predictions are precise, and in the early universe, the observed galaxy population implies dark matter halos that are more massive, more numerous, and present earlier than the halo mass function predicts. This is the mathematical statement of the crisis. The galaxies Webb finds require halos that the model says should not be there yet. Scientists have a few options when a model fails. The first option is to find an error in the data. Maybe the redshifts are slightly off. Maybe the mass estimates are systematically inflated by some observational effect. Maybe lensing by foreground galaxies is making some objects appear brighter than they are. Scientists have been checking all of these possibilities carefully. The data holds up. The errors, where identified, are too small to explain the discrepancy. The second option is to add new physics to the model. Modify the behavior of dark matter in some way that allows halos to form faster. Change the assumptions about how efficiently gas converts to stars. Allow for some additional energy source that accelerates structure formation in the early universe. This is where most of the theoretical work is happening right now. Dozens of proposals have been published. Some tweak known parameters within the existing framework. Others introduced genuinely new elements. The third option, the most radical one, is to replace the model at a deeper level, to question whether lambda CDM itself is fundamentally correct, or whether it is an approximation that works well at late times but breaks down in the extreme conditions of the early universe. Most scientists are not ready to go that far. The model's successes are too broad and too well established to abandon casually. But the conversation is shifting. Papers that would have seemed fringe 5 years ago are now appearing in leading journals. Webb did not just challenge a few predictions, it challenged the reliability of the entire early universe chapter of the standard model. And the deeper it looks, the more clearly that challenge comes into focus. The most intense version of the debate involves something even more fundamental than how galaxies form. It involves the question of whether we truly understand how the universe itself has been evolving since the Big Bang. Not all astronomers accept the crisis at face value. A significant faction of researchers argues that Webb's early galaxies are not as massive as they appear. They are bright, yes, extraordinarily bright, but brightness and mass are not the same thing. The argument goes like this. When you calculate a galaxy's mass from its brightness, you are making assumptions. You assume the light is produced at a steady rate by a normal stellar population. You assume the ratio of bright stars to dim stars follows a standard pattern. You assume the galaxy's light is not being amplified by any external effect. In the early universe, some of these assumptions may break down. Early galaxies may have gone through short, violent episodes of extreme star formation, called starbursts, during which they were temporarily far brighter than their actual mass would normally suggest. A starburst is a burst of activity, not a stable state. The galaxy ignites a huge population of massive stars all at once. These massive stars are enormously luminous but die in just a few million years. During that brief window, the galaxy shines with a brilliance completely out of proportion to its total stellar content. If Webb is catching many early galaxies during the peak of a starburst phase, their brightness would overestimate their true mass significantly. The observed population of massive early galaxies could be a selection effect. Webb is finding the brightest objects at each epoch, not a representative sample of all galaxies. This is a real concern, and it is scientifically valid. The counter-argument is also real. The spectral data from galaxies like MOME Z14 is detailed enough to constrain not just total brightness, but the type of stellar population present. Scientists can estimate the age distribution of stars in a galaxy from spectral features. A pure starburst population looks different from a mixed population of young and old stars. MOME Z14 shows evidence of a complex stellar population, suggesting the galaxy has been forming stars for some time, not just in a single sudden burst. This pushes back against the pure starburst interpretation. The debate is ongoing. It is one of the healthiest scientific arguments happening in astronomy right now. Both sides are working from real data and applying rigorous methods. The answer will likely involve some combination of effects: genuine mass assembly faster than predicted, combined with starburst-driven luminosity boosts that exaggerate the apparent mass of some objects. The honest answer, confirmed by the scientific community as a whole, is that both effects are probably real and probably contributing to the observed population. What remains unknown is the precise fraction each effect contributes. That uncertainty is not a failure of science. It is science working exactly as it should. Observation finds something that challenges the model. The model fights back with alternative interpretations. Careful measurement eventually distinguishes between them. Webb will keep looking. The statistical sample will grow. The starburst fraction will be constrained by better spectral data. The true mass distribution of early galaxies will come into focus, and somewhere in that focus, the answer to how the early universe built structures so fast will become clear. The next step in that clarity involves the most extreme phase of cosmic history, the era when the universe itself was still opaque, and the objects forming inside it were powerful enough to burn a path through it. Picture a star so large that if you placed it at the center of our solar system, Its surface would extend past the orbit of Jupiter. Jupiter orbits the Sun at a distance of about 480 million miles. A star that large would swallow Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter itself, without reaching its outer edge. The first stars in the universe were probably in this size range. Some models suggest even larger. Scientists call these population 3 stars. They are confirmed to have existed based on the physics of the early universe, even though no instrument has ever directly detected one. The logic that requires them is airtight. The Big Bang produced hydrogen and helium, almost nothing else. The early universe had no heavy elements, no carbon, no oxygen, no silicon, no iron, just 2 light gases floating in a dark, cooling cosmos. When the first gas clouds began to collapse under gravity, they had none of the cooling tools that modern gas clouds rely on. Heavy elements and dust radiate heat efficiently and help gas clouds cool quickly, which speeds up collapse and allows the cloud to fragment into many smaller, lower-mass stars. Without those heavy elements, the early gas clouds cooled slowly. Collapse was sluggish. The cloud stayed large as it fell inward rather than breaking apart. The result was a single massive object, forming at the center of each collapsing cloud, accumulating mass far beyond what modern star formation typically produces. Physics simulations, run on some of the most powerful computers on Earth, consistently produce population 3 stars with masses between 100 and several hundred times the mass of our Sunday. Some simulations, under specific early universe conditions, produce objects approaching 1,000 solar masses. At these masses, the stars burned at surface temperatures several times hotter than our Sunday. They flooded their surroundings with ultraviolet radiation so intense it stripped electrons from hydrogen gas across enormous regions of space. Each of these stars lit up a bubble of ionized gas around itself, beginning the long process of clearing the cosmic fog that filled the early universe. Their lives were brief, a few million years at most. Then they collapsed, either in violent hypernovae that scattered enriched material across hundreds of light years, or directly into black holes if they were massive enough. Those that exploded left behind the first heavy elements in the universe: carbon, nitrogen, oxygen, and heavier things still, scattered across the surrounding gas and beginning the long chain of enrichment that eventually produced every planet, every ocean, every living cell. The atoms in your body were forged in stars. The first generation of those stars was extraordinary, and their legacy is written in every galaxy that came after them, including MOME Z14. The specific way those first stars died and what they scattered when they went turns out to matter enormously for understanding the chemistry web is reading across 13 billion light-years of space. A star dies. The universe changes forever. That sentence sounds dramatic, but it is a literal description of what the death of a massive first-generation star accomplished. When a star of several hundred solar masses exhausted its nuclear fuel, the outward pressure that had been holding it up against its own gravity disappeared. The core collapsed in less than a second. The infalling outer layers slammed into the collapsing core and bounced back outward in a shockwave of extraordinary violence. The explosion released more energy in that single second than our sun will emit across its entire 10 billion year lifetime. That energy was not just destructive, it was transformative. In the final moments before the core collapsed, and during the explosion itself, the extreme temperatures and pressures drove nuclear reactions that built elements heavier than anything the star had produced during its normal life. Carbon fused into neon. Neon fused into oxygen. Oxygen and silicon fused into iron. Iron cannot fuse further to release energy, so it built up in the core until the collapse became inevitable. The explosion scattered all of these elements into the surrounding gas. Carbon, the backbone of all known life. Oxygen, the most abundant element in Earth's crust. Nitrogen, the dominant component of the air you breathe. Silicon, the basis of rocks and electronics. Iron, the foundation of every blood cell in your body. All of it came from dying stars. And the very first stellar explosions in the universe were particularly powerful because the stars were so enormous. The hypernovae produced by the most massive population. 3 stars released perhaps 100 times the energy of a standard supernova. The shockwave from a single explosion could compress and trigger star formation in gas clouds across hundreds of light-years of space. This is where the timeline of the early universe starts to make more sense. The first massive stars exploded and compressed nearby gas. That gas collapsed into the second generation of stars faster than it would have through gravity alone. The second generation formed with some heavy elements already present, making cooling more efficient, making the stars slightly lower in mass on average, but still producing enormous and energetic populations. Each generation of stellar death turbocharged the next generation of stellar birth. The chemical fingerprint Webb reads in MOMZ 1.4 is the fingerprint of this process already having run through at least one full cycle. The nitrogen enrichment, the unusual chemical ratios, all point to previous generations of massive stars having lived and died before MOMZ 1.4 lit up. The cycle of stellar birth, element production, violent death, and chemical enrichment is the engine that built every complex structure in the universe. Every rocky planet, every ocean, every carbon-based molecule in every living thing on Earth. And the earliest chapter of that cycle is still running right now in the data Webb is sending back. Every new spectrum from an ancient galaxy is a new window into that first generation of stellar explosions. What those explosions accomplished on the largest scales, how they transformed not just individual galaxies but the entire structure of the early universe, is visible in one of the most dramatic events in cosmic history. You are made of stardust. That sentence gets used so often, it has lost its power. So instead, trace it precisely. The hydrogen atoms in the water in your body formed in the Big Bang, 13.8 billion years ago. The oxygen atoms bonded to that hydrogen were forged in the cores of massive stars that lived and died before our sun existed. The carbon atoms forming the backbone of every protein in every cell of your body were produced in the cores of stars, between 1 and 8 times the mass of our sun, scattered when those stars shed their outer layers at the end of their lives. The calcium in your bones came from supernovae. The iron in your blood came from the cores of massive stars that exploded. The phosphorus in your DNA came from the same violent stellar deaths. Every atom heavier than helium in your body passed through at least one stellar interior before reaching you. This process has a name: nucleosynthesis. It is the nuclear forging of elements inside stars and stellar explosions. It is confirmed physics. The predicted ratios of elements produced by different types of stars match the observed ratios in the universe to extraordinary precision. Nucleosynthesis is the reason complex chemistry is possible. Without it, the universe would contain only hydrogen and helium forever. No carbon to build molecules, no oxygen to combine with it, no nitrogen to make amino acids, no phosphorus to build genetic material, no planets, no oceans, no life. The first stars changed that. Their explosions seeded the universe with the first heavy elements. Subsequent generations of stars processed those elements further, producing heavier and heavier atoms, scattering them more widely with each generation of stellar death. By the time our sun formed 4.5 billion years ago, the gas cloud it formed from had been enriched by multiple generations of stellar nucleosynthesis. The heavy elements were present in sufficient quantities to form rocky planets. Earth coalesced from that enriched material. Life emerged on its surface using the chemical complexity that billions of years of stellar death had made possible. The connection between the first stars in the early universe and the existence of life on Earth is direct and unbroken. Every generation of stellar birth and death contributed to the chain. Every hypernova, every quiet stellar fade, every pulse of element-enriched gas, all of it fed forward through time to produce the conditions that eventually allowed complex chemistry to exist. When Webb reads the chemical fingerprint of Mohm, Z14, and finds unusual nitrogen and carbon ratios, it is reading a record of the first links in that chain, the first time the universe produced the elements that everything else would eventually be built from. The story of how those elements spread across the early cosmos connects directly to another massive transformation, one that reshaped the entire universe, from fog to clarity, from darkness to light, an event that involved every early galaxy, including the ones Webb has found. After the Big Bang, the universe passed through a long, dark age. For hundreds of millions of years, the cosmos was filled with neutral hydrogen gas. Neutral hydrogen absorbs ultraviolet light extremely efficiently. This made the early universe almost completely opaque to the light produced by the first stars and galaxies. The fog was everywhere. Astronomers call this the era of reionization. It began when the first massive stars switched on and started blasting ultraviolet radiation into the surrounding gas. Each star created a bubble of ionized hydrogen around itself, a region where the radiation stripped electrons from hydrogen atoms, making the gas transparent to ultraviolet light. At first, these bubbles were isolated, individual stars and early galaxy clusters carving out small pockets of clarity in an otherwise opaque universe. But the bubbles grew, and they merged as more stars formed, as more galaxies lit up. The bubbles of ionized gas expanded and connected, slowly, then faster. The fog burned away from the inside out, driven by the collective radiation of millions of galaxies pouring ultraviolet light into the surrounding hydrogen. By roughly 1 billion years after the Big Bang, the era of reionization was largely complete. The intergalactic medium, the gas filling the space between galaxies, had been converted from opaque neutral hydrogen to transparent ionized plasma. The universe became clear, and every galaxy Webb has found in the earliest observable epoch played a role in this transformation. Mohm Z14, at 280 million years after the Big Bang, was generating ultraviolet radiation during the deepest phase of reionization. Its population of hot, massive stars poured ionizing photons into the surrounding fog at an extraordinary rate. The bubble of cleared space around Mohm, Z14, would have been one of the first expanding pockets of transparency in a universe still largely sealed by neutral hydrogen. Galaxy Y1, at 600 million years after the Big Bang, sat in a period when reionization was well underway. Its starburst phase was contributing enormous quantities of ionizing radiation to the ongoing process of clearing the cosmic fog. The era of reionization is not just a historical event in the early universe. It is the event that made the universe habitable for future generations of galaxies and eventually planets. Before reionization, intense ultraviolet radiation from young massive stars would have been trapped and absorbed close to its source. After reionization, that radiation could travel freely, influencing the chemistry of gas across vast distances. The structure of the universe we observe today, the web of galaxy clusters and voids, the properties of gas in the spaces between galaxies, all of it was shaped by reionization, and the galaxy's web is discovering pushed that process forward from its very beginning. Understanding when reionization started, how fast it progressed, and what drove it depends entirely on knowing how many massive early galaxies existed and how much radiation they produced. Webb's discovery of more early galaxies than expected directly changes those calculations. The fog cleared faster than the standard model predicted, because there were more sources burning through it, and Webb is not finished looking. 280 million years after the Big Bang is the current record. Mohm Z14 holds the title of the most distant confirmed galaxy ever observed, but Webb is still running. The telescope's science program extends for decades. It carries enough coolant to operate for well beyond its original 10-year mission timeline. Its instruments are still performing at or above their design specifications. And the observational program laid out by scientists worldwide includes dedicated campaigns to push redshift records further and further into the universe's first moments. The theoretical target is clear. Scientists want to detect the first generation of population 3 stars directly. The epoch of those first stellar fires sits somewhere between 100 million and 200 million years after the Big Bang. Webb may not have quite enough sensitivity to reach the individual stars of that era, but it could potentially detect entire clusters of them, or the ionized bubbles they carved out of the surrounding fog. Finding direct evidence of population, 3 stars would close one of the last major observational gaps in the story of cosmic history. It would confirm or rule out the theoretical predictions about their size and luminosity. It would constrain the models of early chemical enrichment that scientists are currently relying on to explain MOMZ-14's unusual composition. The other major observational goal involves mapping the era of reionization in greater detail. By studying how the properties of the intergalactic medium change across different redshifts, Webb can trace the timeline of when the cosmic fog cleared in different regions of the universe. This mapping will reveal how many early galaxies existed at each epoch and how efficiently they were producing ionizing radiation. These observations take time. The faintest early galaxies require extraordinarily long exposure times, sometimes hundreds of hours of continuous observation, to accumulate enough signal for a reliable spectrum. Webb allocates its observing schedule carefully, balancing deep field observations of the early universe with studies of galaxies, stars, and planetary systems much closer to home. Every year of operation adds to the statistical sample. Every new confirmed galaxy at extreme redshift sharpens the constraints on the models. Every new spectrum adds another chemical fingerprint to the catalog. Scientists are also developing next-generation telescopes designed to complement Webb's observations. Ground-based facilities with mirrors 30 meters across, larger than any telescope currently operating, are under construction in Chile and Hawaii. These telescopes will be able to collect spectra of early galaxies faster than Webb can, working in coordination with Webb's unique sensitivity. The picture of the early universe is being assembled piece by piece. Each observation fills in another corner of a map that humanity has been trying to draw since we first understood the universe had a beginning. And at the edges of that map, in the redshift ranges Webb has not yet fully explored, the data is already hinting at something that could force an even deeper revision of what we thought we understood. The universe is 13.8 billion years old. That number is one of the most precisely measured quantities in science. It comes from detailed analysis of the cosmic microwave background, the light left over from 380,000 years after the Big Bang. Multiple independent measurement methods converge on this number with remarkable consistency, and yet, if Webb continues pushing redshift records higher and keeps finding large, chemically complex, organized galaxies closer and closer to the Big Bang, at some point, the timeline starts to strain against itself. Here is the tension. Every galaxy Webb finds at extreme redshift requires time to have formed before Webb observed it. A massive, chemically enriched galaxy at 280 million years old required at least one previous generation of stars to have lived and died before it existed. Those stars needed time to form. The gas clouds they formed from needed time to collapse. Push the numbers and you start crowding the available time uncomfortably. Scientists are not yet at the point where observed galaxy formation timelines contradict the measured age of the universe. The tension is real, but not yet critical. There is still enough room in the timeline for the processes to have occurred, even if the pace required is faster than expected. But if Webb finds a galaxy, fully formed and chemically complex, at a redshift of 17 or 18, the timeline pressure increases significantly. At a redshift of 17, the universe is roughly 180 million years old. A galaxy at that epoch with significant stellar mass and heavy element enrichment would be extremely difficult to accommodate within the current model's timeline, even with the most aggressive assumptions about early star formation efficiency. Some theorists are already discussing what such a discovery would mean. One possibility is that the very first stars formed earlier than current models suggest, perhaps as early as 50 to 80 million years after the Big Bang, under conditions of unusual dark matter density. This would compress the entire timeline of early cosmic history and provide more room for subsequent galaxy formation to proceed. Another possibility is that the measurement of the universe's age itself carries more uncertainty than scientists typically acknowledge. The Hubble tension, a disagreement between different methods of measuring the expansion rate of the universe, has been growing more significant for years. If the expansion rate in the early universe was different from what lambda CDM predicts, the inferred age of the universe could shift. A shift of even a few 100 million years in either direction would dramatically change how comfortable the galaxy formation timeline becomes. These ideas are at the frontier of theoretical physics. They are serious proposals, published in leading journals, taken seriously by leading researchers. They are not answers yet, but Webb's continuing observations will either tighten the constraints or force scientists to examine them more carefully. Every new redshift record Webb sets is a data point in this larger argument, and the argument is pointing towards something that very few people expected when Webb launched. The universe may have been more active, more structured, and more complex in its first moments than any model built before Webb's observations had the right to assume. The universe is not just expanding, it is accelerating. This was confirmed in 1998, when two independent teams studying distant supernovae discovered that the expansion of the universe is speeding up over time rather than slowing down, as gravity would suggest. The force driving this acceleration is called dark energy. It makes up roughly 68% of the total energy content of the universe. Dark energy is one of the most confirmed and least understood facts in physics. Its effect in the modern universe is to push galaxies apart at an ever-increasing rate. But in the early universe, when everything was packed much more tightly together, dark energy's influence was negligible compared to gravity and the density of matter. The early universe was dominated by matter, and gravity drove the formation of structure. At least, that is what the standard model assumes. Some theorists are now asking whether dark energy behaved differently in the early universe than it does today, whether its influence was not constant across cosmic history but varied, whether it could have had an effect on early structure formation that the standard model does not account for. This idea has a name: dynamic dark energy, and it has recently received some observational support from a large-scale galaxy survey completed in 2024, which found hints that dark energy may not be a fixed constant as previously assumed. The evidence is preliminary. It is not confirmed, but it has serious scientists paying serious attention. If dark energy had a different character in the early universe, it could have affected the rate at which dark matter halos collapsed and galaxies formed. A slightly different dark energy behavior during the first billion years after the Big Bang could cascade into significant changes in the predicted galaxy population at high redshift. A separate line of theoretical investigation involves modifying the behavior of dark matter itself. Standard cold dark matter models assume dark matter particles move slowly and cluster easily under gravity. Some alternative models propose warm dark matter, particles that move slightly faster and form halos on a somewhat different schedule. Others propose self-interacting dark matter, where dark matter particles interact with each other in ways that affect how halos form and collapse. These modifications are constrained by many other observations, so they cannot be changed arbitrarily. But within the allowed range of modifications, some variants can produce earlier and more numerous dark matter halos, potentially helping explain Webb's early galaxy population. The honest answer to what explains the faster-than-expected galaxy formation in the early universe is that scientists do not yet know. Multiple proposals exist. None is definitively confirmed. The data from Webb is still accumulating. What is clear is that whatever the explanation turns out to be, it will require changing something about the current model. The question is how deep that change goes. Whether it is a parameter adjustment within the existing framework or the beginning of a more fundamental revision of how cosmologists understand the universe's first chapter, that revision, wherever it leads, will change how we understand our place in the cosmic story. 13.8 billion years of history, and we are somewhere near the end of it. Everything Webb has revealed in its first few years of operation points to a universe that began building complexity far earlier than we imagined. The first stars ignited within the first 200 million years. The first galaxies organized and grew to enormous sizes within the first billion years. The cosmic fog cleared. Heavy elements scattered across space. Generations of stars lived and died, each one enriching the environment further, each one setting the stage for everything that followed. By the time our sun formed 4.5 billion years ago, the universe had already lived 9 billion years of this story. The raw materials that built Earth, the carbon, oxygen, iron, phosphorus, all of it, had already been forged, scattered, reforged, and scattered again through multiple generations of stars, living and dying in galaxies we can now photograph from 13 billion light-years away. We are late arrivals to a universe that was already ancient and complex when our solar system was born. This shifts something in how the story of life fits into the cosmic picture. If galaxies formed faster, if chemical enrichment proceeded earlier than expected, then the conditions for rocky planets and complex chemistry appeared earlier in cosmic history than previous models suggested. The universe may have been capable of hosting planetary systems similar to Earth much earlier than we previously estimated. This is a theory grounded in the logic of the data. It is not confirmed, but it is a serious inference that astronomers are beginning to explore. The implications extend further. If chemical enrichment proceeded efficiently in the early universe, and organized galaxies existed within 1 billion years of the Big Bang, then the potential window for life to arise somewhere in the universe is longer than we thought. The universe had more time, more opportunities, more iterations of stellar chemistry than the standard model's timeline suggested. We do not know whether life exists anywhere else. That question remains completely open, but the universe Webb is revealing is a richer, faster, more productive place than the one scientists imagined before December 2021. MOME Z14's light left its source 13.5 billion years ago. That light crossed the universe, stretched by cosmic expansion, changed in wavelength, carried across voids between galaxy clusters, and arrived at a gold mirror floating 1 million miles from Earth. Scientists decoded it, read the chemistry, traced the fingerprint back to a galaxy formed in the universe's infancy, and in that decoding, they found a story that reaches all the way forward to us. The carbon in your body has a history. That history begins in the cores of the first massive stars in the universe. Stars that burned for a few million years in young galaxies, some of which looked remarkably like the ones Webb is photographing now. Stars whose deaths scattered the raw material of everything you are made of across the early universe. The universe is 13.8 billion years old. You are its latest and most complex chapter, and Webb is still looking.